6G Integrated Sensing and Communication, or ISAC, merges radar detection and data transmission into a single unified waveform. To accurately track an airborne object, the base station has to physically focus its transmit energy directly onto the target, forming a concentrated beam to read the returning echo. This creates an immediate physical paradox when the target you are actively tracking is a malicious drone trying to steal your data. By successfully tracking the drone, the network is deliberately bathing the eavesdropper in a highly focused radio frequency. You are inadvertently handing the adversary a pristine, high signal-to-noise ratio channel to intercept your sensitive transmissions. To solve this conflict, researchers map the interaction as a non-cooperative Stackelberg game, a mathematical framework built to model asymmetric sequential competition. In this framework, the malicious UAV acts as the leader. It dictates the engagement by proactively maneuvering through three-dimensional space, actively hunting for the best physical angles to intercept the signal. The legitimate base station is relegated to the follower. The network cannot physically move. It must constantly react, shifting its power allocations and beamforming configurations based entirely on where the drone chooses to fly. This pits a physical drone navigating slow, real-world aerodynamics against a digital algorithm optimizing invisible radio waves at the speed of light. A standard optimization equation cannot solve for both sides of this conflict simultaneously. Achieving a mathematical equilibrium requires splitting the system. The base station's defense relies on solving a highly non-convex optimization problem, while the drone's spatial attack demands the sequential foresight of deep reinforcement burning. The base station, acting as the follower, has one primary operational objective in this game: to minimize the total network power consumption, but it must stay within strict operational thresholds. The base station has to maintain hard lower limits on its communication secrecy rates, while keeping the variance of its radar range estimation under a rigid ceiling, a metric known as the Kramer-Rao lower bound. To execute this, the station injects dedicated artificial noise into the transmit signal, actively degrading the drone's ability to decode intercepted data. Simultaneously, these artificial noise vectors increase the degrees of freedom in the transmitted waveform, boosting radar accuracy enough to satisfy the strict tracking threshold. Balancing minimum power against strict security and tracking constraints creates a highly non-convex mathematical landscape. It is a space full of jagged local minima that instant linear algebra cannot parse. To bypass this geometry, the follower uses a strategy called successive convex approximation, or SCA. Instead of trying to solve the entire chaotic surface at once, the algorithm uses a first-order Taylor approximation to carve out a smooth, localized U-shaped convex bowl around its current position. The system calculates a direct path to the exact bottom of this new bowl, locking in a highly efficient local power allocation. Next, the station configures the physical antenna beams, a process hindered by rigid rank 1 matrix constraints. To clear this hurdle, it applies semi-definite relaxation. This relaxation strips away the absolute rank requirements, converting an impossible geometric calculation into a solvable matrix inequality. The SCA algorithm fires in a rapid continuous loop. It recalculates these Taylor approximations recursively, moving step by step until the power and beamforming variables lock into a stable configuration. Because the localized math is relatively light, this executes in fractions of a millisecond, deploying an optimized radio frequency defense for a specific snapshot in time. But the SCA algorithm has a fatal blind spot. It only reacts to the environment in that exact millisecond. Generating a perfect instantaneous radio defense serves no purpose if the system cannot anticipate where the drone is going to fly next. This brings focus back to the leader. The drone is physically maneuvering through the air, hunting for the clearest possible channel to intercept the signal. Its objective is to maximize the data it steals while minimizing the physical aerodynamic power required to keep its rotor spinning. You cannot optimize an aerodynamic flight path using instantaneous snapshots. The drone must plan sequentially, making moves now that set up optimal reception angles 30 seconds in the future. To map this, the drone's spatial environment is structured as a Markov decision process. The state space defines the drone's exact 3D coordinates, the remaining flight time, and the base station's last deployed defense. Within this grid, the drone calculates an exact action space. It can move up, down, forward, back, left, or right, selecting between 3 distinct speed tiers for every physical move. Restricting the continuous airspace into a rigid grid of states and actions forces the drone to evaluate the long-term aerodynamic consequences of its trajectory. It is the perfect environment for deep learning. To navigate this grid, the drone relies on a double deep Q network, or DDQN. Standard Q learning struggles in highly dynamic environments due to overestimation bias. An agent will hit a mathematical anomaly, assume a terrible flight path is highly valuable, and ruin its trajectory. To eliminate this bias, the DDQN architecture splits the processing into two distinct pathways, the online network and the target network. The online network has a single job: look at the current state of the airspace and select the next immediate flight action, but it does not grade its own homework. The target network steps back to independently evaluate the long-term mathematical value of the action the online network just selected. The system then logs these outcomes in an experience replay buffer. This buffer acts as a vast database of past state action transitions. The drone randomly samples from it, learning from thousands of previous flight mistakes without having to physically recreate them. Periodically, the target network synchronizes its parameters to match the online network, locking in verified progress and stabilizing the learning loop. By running this architecture across thousands of simulated episodes, the drone maps the environment and predicts the base station's defense strategy over the length of the entire mission. The bipartite system is now a closed, infinite operational loop. The drone moves using its DDQN algorithm, the base station reacts using successive convex approximation, and the environment feeds the success or failure back. This chart tracks the return over the training episodes. Initially, results are chaotic and returns crash, but at the 500 episode mark, lines flatten and stabilize as the agent maps an optimal trajectory. The blue line conserves power, while the red line maximizes eavesdropping utility. This exact point of graph stabilization represents the mathematical end state, the Stackelberg equilibrium. In reality, this means the conflict is perfectly balanced. The drone discovers its optimal attack vector, but the base station perfectly anticipates it, locking the adversary inside a calculated cage of electromagnetic interference. Securing a 6G network requires discarding static defense models. When the physical world and the digital spectrum merge, true physical layer security must be fought and won as a highly dynamic, multi-domain algorithmic game.